the register R0 is saved, and it is then used to load the status register into register R0. So let's see, which is this particular command over here. Then we are going to actually disable all the interrupts, so that this will not be interrupted at all by hardware events. And now we have the status register in R0, so we push R0 out, and then R1, and so forth. And the compiler is always setting R1 to 0, so we'll do that too. So we clear R1, but all the other registers are simply pushed out to R31. And then we need to do a few extra things, which is stated over here. So let's see what's happening. Oops, what did I do? Oh, there it is. So the process interrupts are disabled. I just explained it to you. And then the code generated by the compiler from the ISR C source code assumes R1 is set to 0. So that's what we have also done. Then we get all the remaining processor registers saved in numerical order. So that is what I just was talking about. So we're now at this particular spot. We have just finished this. And we are going to now look at the stack. So the stack of the task being suspended now contains a copy of the task's execution context, because we pushed all these context, all these register values to the stack. So now the kernel stores the stack, the kernel stores the task's stack pointer to the context. So the context can be retrieved and restored when the task is resumed. So what the processor needs to do is it needs to read that stack pointer and put it in that stack control, that task control structure. So that's what's going on over here. So the processor register is loaded with the address to which the stack pointer is to be saved. So that's what we see here. Sorry, this is the wrong slide. It's going on over here. We have some loads over here, right? So we have the stack pointer goes in here. We have the low part and the high part. So first the low part, and then the high part is being read into R0. So anyway, that is how it works. So the stack pointer is now saved. First the low byte, and then the high nibble. So this is the code for doing a context save. Now we also have code for restoring the context, and everything is done in reverse. So the stack has all that material, and now you simply know that you first can get the stack pointer. You will manipulate it in the proper way. Then you can pop off the stack all the register values. The R0 is going to be actually your status register. And then after that you have the actual value of R0 that you popped the very first time, that you pushed the very first time. So this is a restore context. So that's all in the code. And now we see that if we have a timer 1 compare a vector interrupt service routine with the ISR naked command, we have now our own save context and our own restore context. But notice, which context are we going to restore? Well, here we have the array of all the tasks, and we have, we store the current stack pointer in the TCB array to retrieve it later, so it's important. And then we switch to the kernel stack for scheduling computation. So the current stack pointer becomes the kernel's one. I forgot what this means. Then we call the tick function, the increments, so this increments the kernel's tick and picks a new task based on a scaling policy. So that's something that you will have more guidance over to how to set this yourself. Then we store the kernel's latest stack pointer. So we do this. Then we retrieve the stack pointer of the next task. That's what we do now. So you have computed which one is going to be the next task in this piece of code. And now you restore that particular context for that next task. And then you have the return instruction. So now the context switch has occurred on this tick. Alright, so now we're getting to pretty much the last slide. So now how do we look at a piece of main code? So you initialize your usual stuff. You have to initialize the kernel. This is how we write it out. You can register tasks with task periods and different tasks. And then you can just run the task that will effectively call the real-time operating system to do its scheduling of all those different tasks that you have registered and continuously execute those. And notice that this will actually never end. You'll never get into this while loop because this will go on forever. So this is effectively what you will have in your assignment. So you have a piece of code that contains all this stuff, and the assignment is going to be about working on your own scheduler. So let's have a look whether I can find that. Maybe not this one. Maybe yes, actually. So here we have effectively the first part of the assignment for the real-time operating system. This is just the slides for the assignment. So here we again talk about the execution context, saving the context and how that works and so on, which I detailed just now. Then we have the timer 1 ISR, the scheduler task. You have these helper functions. So there's a little bit more here. So what we see here is that so what's going on here? So increment the tick count and check to see if the new tick value has caused a delay period to expire. This function call can cause a task to become ready to run. So you increment the tick. So that was the previous procedure that we talked about actually, and then figure out whether a context switch is required and do so. So how do you implement this? Well, for example, you want to implement round robin scheduling, so you call this particular scheduling policy. But you can replace this with your own scheduling policy. That's effectively what you can do. So if the main task again, which is the main program again, that's the same as before. And in task 1, you're effectively going to download all this material. So this is a simple OS kernel, the one that we just actually detailed throughout this lecture. And what you're going to do is you initialize the kernel in this project with different values of what this could be, and observe the behavior for the output printed on the UART. Change the delay inside task 1 and task 2 and observe the behavior of the output printed on the UART. So you have already 2 tasks in this packet, right? And you're going to change the delay to just find out what kind of pattern do you see. When is task 1 executed? When is task 2 executed? Do they actually meet deadlines and so forth? So you want to answer, for example, why do you sometimes see task 1 and or task 2 being misprinted actually? That's another thing on the UART. That's kind of interesting too. So that is somewhat unrelated, but it has to do with the overall execution where you do see interrupts appearing. So I'm curious what you will find out. Then implement a new function called scheduler rate monotonic in the kernel.h that implements rate monotonic scheduling. So you're going to make appropriate changes, and you're going to replace the round robin by the rate monotonic scheduler, and now you're going to have a look what's happening now. So that's the experiment that you're doing. So you're not going to write your actual real-time operating system, but I did explain in this lecture all ingredients that you need to put in. Actually, it's quite cool. It is difficult to make it all work properly together, but I hope you really got the ingredients so that it's not a black box for you anymore, and you can actually talk with others about this. So have fun with this exercise, and the next lecture we will be talking, I think, about the other part of the exercise. I think FreeRTOS or maybe something else, but we will figure it out. And then you are ready to do the other part of the assignment for real-time operating systems as well. Cool.